record before I forget. All right. I had a question. What was the first question there?
How far are we? What's the midterm inclusive of? Like, are we going till lecture 15 or?
It's going to include everything up to and including all of the lectures that have been posted to date, which is, I think, 15 center of gravity. I believe is whatever that last one is.
Let me see. Oh, so it's posted. Yeah, 15.
Yep.
So
Yep.
it means we're doing chapter 13 too.
Pardon?
It means we're doing chapter 13 too.
Yes, but not all of 13. Because all the equilibrium stuff, we will be on the next one. So center of gravity will be on there, but whole body equilibrium and mass and joint level equilibrium, which I mean, they're up, but I haven't posted them because they're next week's. So I'm just about to release them. Again, I will be releasing the lectures for you to see, but they won't be on the midterm.
Okay.
So the equations of static equilibrium portion of 13 will not be, but center of gravity will be, and understanding how muscle works will be.
Okay.
Stability and balance won't be. That's later. That'll be later. So it won't be. That's the very last thing on 13. So some of 13 will be on it, and some of 13, kind of half of 13 will be on it.
Because the practice questions that you gave us for 13, some of them cover the parts that we haven't actually learned.
Such as?
Since we're doing like almost all of them, I just want to have to, since it's covering.
Which ones are on the midterm is basically what you want to know.
Yeah.
So one would be, I don't know which ones I assigned you, but one, I'm just looking at the additional. One would definitely be, two, again, that's not anything that you can get an answer to that gives you an answer, so that's not easily. Three wouldn't be. I hate three. Three's a really poorly done question because you can do it wrong and get the right answer. And four won't be. 3 and 4 won't be. Six will be. 8 will be. 9 not. And 10 will be. 10 is just a sum of forces. Well, don't worry about 10. Actually, 10 is 10's an interesting question. It's a question that there's a portion of it that is truly what we've learned in this class, and there's a portion of it that is just advanced math, and I don't require you to do it. But anyway, somebody always asks me it, so I will do it at some point. So does that help? Just gives you a sense of
what about
on the introductory problems?
Yeah.
Well, one is definitely yes. You should know how to do that because that's basic torque. Same with 2. Same with 3. You should be able to do. Not really 4. 5, yes, because you've done those kinds of problems already. 6, yes. 7, yes. 8, yes. 9, yes. And 10, yes, because that's center of gravity.
Okay. Thank you. I have one last question.
Okay.
Sorry.
Those were
So
chapter.
chapter 13. For chapter 12, there are some questions that talk about kinetic energy, mechanical energy. Like, are we required to know that since you
No.
did it? No.
I think I say it in the list of problems that there are questions on there that are listed as being done by energy. I will not require you to do that. I would love to have enough time to get to energy. I don't. So giving the priority of things that I would like you to know by the end of this class, energy turns out not to be the priority. So the only part of energy that we cover is potential energy, and we cover it in terms of stability and balance, because it does have a role to play there as to why. Well, the lecture's not posted, but in terms of the whole transfer between potential energy and kinetic energy, I'm not requiring you to do those types of problems. However, and I think I put an asterisk beside these on some of the problems and say, you know, the parts of the question, there are some parts of the questions that you can do equally easily using projectile motion. And so, for example, chapter 12, let me see if I can find one. 8, additional problem 8, which talks about how high the center of mass could go in the jump. That part of the question you can do with your own using projectile motion. So you do not need to use energy to do it. You can use, if you know what the takeoff velocity is in the vertical direction, you can calculate how high up something goes, right?
Yeah.
So you don't need to use energy. So I'm not going to ask you what the kinetic energy of the body is at takeoff, but I could very easily ask you how high up it went.
Okay.
Okay. Carissa.
Yeah, so another question I had, like, what about the momentum questions on chapter 12? Should we know those questions?
No, not yet. You do not need to know momentum yet because you haven't done momentum yet. I combine linear and angular momentum together. We don't ever do that, the collision piece. Love to, but again, only so much time in the term. But the linear and angular momentum get done together, and they get done in the last third of the class. So they are not, you don't have to worry about that. Okay? You will later, but not now. I thought well, yeah. So you just follow it is. Okay. Tanaz? It's all one word, so hopefully.
Yes, how it's as I don't know why there's not enough space.
Space.
Is it possible that we do chapter 12 introductory problems 5C?
Let me just, I'm just going to find a pen here so I can write these down. 12 introductory 5C.
Yes, please.
Okay.
Thank you.
So we have, oh, it's a friction problem. Very important to know friction. So a football player pushes a 670 Newton blocking sled. The coefficient of static friction between the sled and grass is 0.73, and the coefficient of kinetic friction between the sled and grass is 0.68. And basically answer the same two questions with the 100-kilogram coach standing on the back of the sled. Hold on, and I will share my screen with you. Let me just get a whiteboard up. And clear it off. There you go. So you should be able to see the whiteboard, and you're about to see my ceiling. I guess it's just easier to write with a pen. Okay, so we have a tackle sled. Which I think, has some cushioning on it. And slides across the ground. And you've got the force of the football player is going to exert a force there. To try and get it to slide. And there's going to be a normal force here. And there's going to be a force of friction here. And we have the coach standing here. And so we're going to have a force due to gravity, or a weight of both the sled plus the coach. And this is the only difference. If you do A and B the first time round, it's just going to be the weight of the sled. If you do it the second time round, it's the weight of the sled plus the coach, because the football player's hitting the sled with the coach standing on it. So the weight of the combined is what's going to be important. The sum of the forces in the y direction, let's start with that, are going to equal mass times the acceleration in the y direction. And this is going to be 0 because it's not going up or not going down. We're assuming he's hitting the sled while it's on nice level ground. So that's all going to equal 0, which means the normal force is going to equal the weight of the sled plus the coach, which is going to equal 670 newtons. We already know how much that weighs, plus the weight of the coach. Well, it's 100 kilogram coach, but we actually have to put that into force, right? Heavy coach. So somebody want to do that math for me? It'd be 100 times 9.81 plus 670. Be roughly 1670, but
651.
651.
1,000.
1,651 newtons. That sounds about right, because 10 times 100 would be 1,000. 1,000 plus 670 would be 1651. So we know what the normal force is. The force due to static friction. So this is it. And this is important that it's maximum static friction. So that is the force that the player would have to exert to get these sled started. Is going to be, it has 0.73 times 1651, which will be, that's newtons, this is unitless.
It's 1,205 newtons.
Perfect. Okay. So, the force of the football player has to be greater than 1,205 newtons to get it started. The force of the kinetic friction is equal to 0.68 times 1651 newtons, which equals
1,122 and 7.7.
7 newtons. Okay, perfect. So this gets it started. Keeps it going. If he does less than, if he does less than 1,205 initially, it just won't start moving. Once he hits 1,205 and goes over 1,205, it will start moving. But then if he doesn't maintain 1122.7 newtons or higher, if it's higher, it will accelerate. If it's exactly 1,122.7 newtons, it will keep going at a constant velocity. And if it's less than 1122.7, it will slow down and stop eventually. So he has to keep going at or greater than 1122.7 to keep moving. And it really is, equal to or greater than. Any questions on that?
No, thank you very much. I got it.
Okay. Okay. Brenda.
So sorry, I had a question with regards to the what you just solved.
Oh, yes. Sorry.
No worries. I solved it, but I did it in a different way. I still got to the answer, but I did it in a different way, where I had Fm is equal to mu s R. It was an equation given in a textbook. And then I just added the weight of the coach after calculating for previous A and B to get to the answer.
Say that again. FM equals.
It's like the symbol mu. It's like a, I don't know how to describe it. It's a symbol in the textbook. I can redirect you to, so sorry. I can redirect you to.
The
Like,
force of the
hey.
friction equals that symbol.
Yeah, that.
That symbol is the symbol for, that's what I used. That's exactly what I used. It was not different if that's what you did. And then you put either R here. I use the FN, which means normal force. Sometimes they use R for meaning normal force. It's the same thing.
Oh, okay. Never mind then, sorry.
So totally the same. And all I did was to find the maximum static friction was do the coefficient of maximum static friction times R, which happens to be, in the case of the coach waiting there, the weight of the sled plus the weight of the coach, which is the 670 plus just under 1,000 newtons, 981.1 newtons. So yeah, that's exactly what I did. No different.
So sorry, I mistook it for an M.
Oh, what the the coefficient of friction?
Yes.
Oh, sorry. Yeah, that is the symbol for mu, which is the symbol for friction, coefficient of friction. Oops. Okay, I think if nobody else has any questions specifically on that question,
No.
then Brenda, you're up.
I have a few questions. So they're from chapter 13.
Okay.
Question 8 and 9 in the intro,
Okay.
and then 6 and 8 in the additional problems.
Well, let's start with a couple of those, and then we might just see if there's where other people are, and then go back. But we'll see. Start with that. So. Eight and 9 in the
Intro, yeah.
okay, so eight's a pretty common question that we started in with chapter 6. Using a diagram, identify the magnitudes of the rotary and stabilizing components of 100 Newton force that acts at an angle of 20 newtons to a bone. So,
Professor,
yeah.
Can you also go over that stabilizing and dislocating? I kind of don't get how those two work.
Yeah, I will go over both parts of that. So let's just, and in fact, I can extend 8 and go into more examples. Let's just use, for example, the biceps coming into the forearm, just because it's easy. So if I have the forearm in hand, I've cut at the elbow, and I have my muscle, which is coming in at an angle here. So this is an angle of insertion of 20 degrees. There's my center, joint center, and and my angle of insertion. My distance of insertion would be from that center of rotation of my elbow to where it inserts. We don't need that for this question, but we will. This would probably be a case where my arm would be almost straight out for the biceps to be pulling at that angle. When I do that, and so remember, muscles create tension, so the force itself is going to be there. That is the force of the muscle. It is pulling on the bone. It is pulling in the direction from the, in this case, from the insertion towards the origin. A muscle's angle is going to depend on the joint angle that you're at. And it's going to give you this angle of insertion. So that's the angle it comes into the bone at. When it happens, you can think of you can split this into two components. We've been splitting things into components from the third lecture in this class. And there's a reason why I harp on splitting things into component. And this is an excellent example of it. You can take that muscle force and think of it as being two forces. One, which is the rotary component of the muscle force. And so that would be the force component that is 90 degrees to the bone. And one, which is the stabilizing component of so you can see that's the distance out that way. So I am literally splitting that muscle force into two components. The stabilizing component, this guy right here, goes right through the joint center, which means it has zero moment arm for the joint center, which means it does nothing for rotation. It does nothing to make your forearm rotate around your elbow. Not a thing. All it does is directly pull your forearm, in this case your ulna, into the elbow joint itself, right? And that's why it's called stabilizing, because if you pull two bones together at the joint, it sort of increases the force in that joint, and that just stabilizes it. It makes it harder when you pull those two bones together. You are essentially increasing the normal force between the two joint surfaces, and therefore friction is higher, right? We've just talked about friction. Friction is going to be higher. So it's going to be harder to slide the two joints apart when you do that, which makes it stabilizing. It helps to stabilize the joint, makes it almost more like a rigid body between the two bones. Now, the angle of insertion is between the bone and the muscle. And so when it's 20 degrees like that, in this particular case, that was considered to be 100. So this guy is adjacent to that 20 degrees. So that's going to be 100 newtons. I'm just taking the components times cos 20, which if I just look at the answers here, somebody can compare, is 94 newtons. And I would suggest somebody plug that into the calculator and make sure they got it right. And this part is, of course, basically opposite. So when we take our two components, and this is going to be 100 newtons times sine 20, and that would, according to this one, be 34 newtons. Does that make sense, sine and cosine-wise? Well, yes, it does make sense, sine and cosine-wise, because at 20 degrees like that, you would expect your stabilizing component to be bigger than your rotary component. So the rotary component is the portion of the force that's acting 90 degrees to the bone, and it's going to act, its role is completely to act around the, to cause rotation around the joint center. And the stabilizing component pulls into the joint and therefore stabilizes it. You could have a situation, which somebody asked me. I mean, there's basically three scenarios. There's that with the muscle acting directly at 90 degrees, where you have an actual angle of insertion of 90 degrees. In that case, there is no rotary, or there's no stabilizing or dislocating component. It's all rotary because it's already all acting 90 degrees to the bone. And then the third situation is the one, and to do this, you sort of have to imagine that your arm is it's hard to get that so you can see it, but it's really bent a lot. And so the actual muscle force is acting in this direction. And your actual angle of insertion in that particular case technically is going to be, well, it could be something over 90. So it could be, for example, 150 degrees. That would be an example of the muscle pulling at that point. And again, yeah, in the case of the biceps here, it really is a case where your muscle, where your joint angle is really small, really small. If you considered straight out 180, then it would be here where it'd be really small. And so in that case, you've got, again, you've got a rotary component, or sorry, you've got a component along the bone, and you've got a component that is acting at 90 degrees to the bone. So this is your rotary component. And this is your dislocating component now. Why is it dislocating? Is because this component of the force actually acts to pull the forearm away from the elbow joint. So literally the ligaments in the elbow joint are being stretched because there is this component of the muscle force that is pulling the bone away from the joint. There's not all that many scenarios in the human body where this happens. Biceps is one of them. If you try to contract if you totally bend your elbow and then try and contract your biceps, you will actually kind of feel it in your elbow because it's pulling away from the elbow joint if you do that. And that is the difference between the stabilizing and the dislocating components. Any questions on that one?
No, I get it. No.
Everybody's good there? Okay, again, remember.
I have a question, sorry. If the joint is like elbow is fully extended, so we don't have any rotary component of the force, right?
Fully extended for the elbow is probably more of an example of this guy. This one right here pretty much comes when your elbow is just under 90 degrees. Think about it, because remember, it's got to go from your shoulder joint, the biceps notch, down to where it where it actually inserts on the bone in the forearm.
Mhm.
So to get this 90 degrees, you are in a situation where your elbow is something 90 degrees-ish. It's not quite 90 degrees, it's a little less than 90 degrees, but you get my idea.
Mhm.
So that's where you get this guy. So this one right here is the one where you're fully extended.
Oh, okay. Thank you.
Any other questions on this one? And again, remember, for the purposes of this, I cannot, when I share my screen, I can't see the chat, so you have to unmute and talk to me. Okay. Let me clear that one then. 9, which was the 10-kilogram block sitting motionless on a table in spite of an applied horizontal force of 2 newtons. What are the, this is a good one for understanding friction. You have a box. It has a weight. There's going to be a normal force. There's going to be a frictional force. And there's going to be an applied force. It says the 10-kilogram box. So because the 10-kilogram box, this also equals R, by the way. It's semantics, but R and F normal, same thing. As we've talked about several times, if it's not accelerating up, it's not accelerating down, then the weight is going to equal, and you're on a horizontal flat surface, is going to equal your R. So R is going to equal 10 kilograms times 9.81 meters per second squared, or 98.1 newtons. And the force of the friction, the other very key word in this question is motionless. And as I've said before, when we talked about friction, the actual force of friction equals the applied force. So if you looked at the forces that are in the horizontal direction, so the sum of the forces in the horizontal direction equals mass times the acceleration in the horizontal direction. It's motionless, so we know that that is 0. And the frictional force is equal to the applied force when it's not moving. When it's not moving, the basically the applied force equals the frictional force. And we've talked, and the frictional force just keeps getting bigger and bigger as you increase your applied force. If I increase my applied force, my frictional force gets bigger and bigger until I hit that maximum static friction, which clearly we haven't hit yet because it's motionless. Once I hit maximum static friction, then it just drops down and stays constant at the kinetic friction. But while it's still not moving, the two are equal. Any questions on that one? No? Okay.
I have a question. When we draw free body diagram, is it possible to draw it from just all the forces from the center of gravity? Otherwise, it looks like a bit messy.
That is something that I know people have been taught in high school. I know people have been taught that in high school, and I'm going to say no. The reason is it works fine for a situation where there is no torques, where there's no rotations. It does not work. So if I take that applied force and I put it up here, for example, and
I see what you mean.
I'm actually creating a torque around the system, which if I had put this force acting at the center of gravity, you would not see that torque. So you have to, in this class, it's really important that you put the forces where they are actually acting. So in the direction they're acting and the point of application where they're acting, because that's what gives you the, that's what, you know, when you add them all up, if it's going in the X direction and something else is going in the X direction, it doesn't matter where they are. You just need to look at which direction they're acting. But when we go to the point where we're talking about torques, then it really is important in terms of which direction they're acting, or where they're acting, because you will not get a moment arm if you put them right at the center of gravity.
I see. Thank you.
You're welcome. It's a very common one I get. So there you go. Any other questions on 9? Okay. Additional problem 6. Let's see if I have it. Oh, there it is. There's the page. Oh, yes, that's a good center of gravity one. Very important. Okay. So this is chapter 13, additional problem number 6, which is a person picking up a suitcase. So this person weighs, I'm sure that's not where their center of gravity is, but we aren't worried about that, or in terms of height. And they're going to pick up a 180 Newton suitcase. So you can kind of imagine that that is now being held here on the person's hand. And they don't lean, so where their own personal center of gravity is stays the same. And so that is 20 centimeters. We're trying to find the, if you think of this as having a X, Y, theta plus, the only thing we're worried about is how much it shifts to the center of gravity of the combined system shifts towards the suitcase. The person themselves, where the center of gravity is, stays the same within the person, because it clearly says in the question, the person doesn't lean. They're in the same posture they were in before they picked up the suitcase. So basically they picked it up and they returned to that same posture. So we're looking for the combined center of gravity of the system. And ideally we would want to do this, we need to know, we're going to be using the equation X C of G equals the sum of the masses times the x's, so, which in this case I is equal to 1 and 2, 1 being the person, 2 being the suitcase, and divided by the sum of the masses. So that's the equation we need. The masses themselves, pretty easy. Now, in this equation, I am letting you know you can have mass, you can have weight, you can have mass fraction, which we talked about in, for example, if you're combining different body parts, I could talk about what fraction of the whole one body segment is. And I could do that. The key is they all have to be the same. So if I used my weight in here, then I would have to use weight in here. So they all have to be, if I use mass here, then they'd have to do mass here. Why is it that they can be the same? Well, it's because mass literally is their weight divided by 9.81, right? And this one would be weight divided by 9.81. The 9.81s would cancel, and I would still, you know, so if I had used weight in here to begin with, it would be fine. I just want to, you know, you can take the time to switch the weights to masses, but you don't have to, as long as you keep them all as weights or all as masses, you're fine. So these ones are easy. So you have your 600 and you have your 180. So your combined is going to be 780, right? But where'd you get your x's? That's the more how do I get it part. Well, in order to get x in this free body diagram, I have to decide on where 0 is. Well, a very logical place to have 0 is directly under the center of gravity of the person. So that is 0x. That's x equals 0. This is x equals 20, right? Because the question asks you, how much does the center of gravity of the person shift from before they hold the suitcase and after they hold the suitcase. So it's very logical to have 0 right under the center of gravity of the whole person, in which case your xc of g is going to equal 600 times 0 plus, because we're adding them together, 180 times 20, and that's in newtons, that's centimeters, all divided by 780 newtons. This will, of course, go to 0, so we're left with, correct my math if I'm wrong here, but 3,600 divided by 780.
That's 4.61 centimeters.
Which equals 4.61 centimeters. And this is newtons, centimeters. That was a centimeter. And this was newtons, so the newtons would be canceled and I'd be left with centimeters. So that's how you do it. You could have, if you wanted to, chosen over here, you know, let's say this to be 0 and this to be 100 and this to be 120. And what you would end up with would be, if you did the math, take the time to do it just so you can prove it that I'm not making it up. If you did that, then your xc of g would be 104.61 centimeters, which is 4.61 centimeters greater than the original 100 that it was. Obviously, it's a lot easier to have called it 0 in the first place, but there you go. Any other questions? Remembering again, you have to unmute and tell me because I can't see chat while you're doing this. Okay.
Can you please add question number 10 and 7 of the introductory problems to the questions?
Well, I have people who are in line. I'm not quite sure where you are, but
Professor, I have a question about this. How did you get the 104.61?
So that was if I made 0 over here, so that the person was actually, their center of gravity was at 100, and the center of gravity of the suitcase would then be 120. Does that make sense?
Oh, okay. So it depends on how you define your x.
It's defined at some point in this problem. You had to define an x. Okay. The easiest place to define your origin for your x is right under the center of gravity of the person, so that is 0. And then the answer you come out with is the final answer. If you had defined some other place as the origin for your x in order to get that x, you still would have found a center of gravity that is 4.61 centimeters over from the center of gravity of the person to begin with. Does that make sense?
Yeah.
I'm just illustrating that you could have done it that way. I don't think you want to do it that way, but you could have done it. You then have to do a second step of saying, okay, the new location is minus 100. So either way, you're going to come up with 4.61, but you need to do that extra step on that one. You don't do that, but you got to remember that if you were doing this in a motion capture system, you actually might be in that scenario because, we've talked about in motion capture where you have that X and Y grid. There always has to be an origin, a place that we call 0, 0, 0 that we take our measurements from. Any other questions on that one? I'm just going to stop sharing for a second because I know there's been I think Amos has had his hand up the longest. Before I go to question 8, I'll just ask which question you would like me to do.
Yeah, it's just for clarification. For question 4, additional problems on chapter 13, I want to make sure if I'm getting the diagram correct. So how I visualize it is that extension of the triceps would be causing a downward force, and you're trying to make sure that the vertical forces will be the net of 0. And then I think the scale is doing an upward force, and then the downward force would also be the weight of the arm.
Which question is that again?
Additional problem 4, I believe, on chapter 13.
Yes. Now, to be fair, that one won't be, if you were, I'll just do the free body diagram for now. There won't be, we're not going to have that's joint equilibrium, which we'll do next week, but just so you can see it. And work from it because I love this problem. So you've got your forearm and hand. You have the force of the scale on the hand. You have the weight of the forearm and hand. Technically, you have joint forces here. Sorry, that's pretty not well done. You have the elbow here. Realistically, when your arm's in that situation, your elbow is actually your elbow is actually the triceps acts behind your elbow. So you've got your joint forces here. Not that you have to worry about them for this question. And you have the force of the triceps acting here. It's in a situation where it's 90 degrees. Does that help? And of course you're...
Yeah, the only thing is that in order for me to calculate it, I had to use, let me see if I can. I used the force of the triceps equals the torque of the upward scale minus the torque of the weight of the forearm and hand divided by the moment arm of the triceps. And I'm not sure if that's correct.
Why wouldn't it be?
Because the way that you draw the forces is a bit different. Because the way I calculate would be torque upwards of scale would equal to the torque of the triceps downwards and the torque of the weight of the arm and hand.
I think you're switching up, and this is a really important concept. I think you're switching up torque and force. Because if you take your torques around the elbow, this is an equilibrium problem, so this one really realistically will be next time. So your torque created by the weight. So if I removed, if you just think, if you put a pencil over top of your drawing of the forearm, just literally, and you hold on where the elbow is. So that's where my elbow is. The weight is going to rotate it this way, which, as I've drawn it, would be a clockwise rotation, and so it would be a negative. The scale force, if I push up on it, is going to rotate it counterclockwise, which is going to be a plus. The triceps, as I've drawn it, if I rotate on it, even though it's pushing up, it actually creates a negative rotation. You see, it creates a clockwise rotation as I've drawn it. So it actually is negative. It is the same sign in terms of direction. When I put it into my equation, it's going to have the same sign as the weight portion because it's going to try and rotate this clockwise. You should always, wherever you're taking your torques around, you put your pencil on top, you hold it. This is again another reason why somebody asked me earlier whether you could have your forces acting at the center of gravity, and the answer is no, because what you want to be able to do is put your pencil or a ruler or something over top of your free body diagram, hold on to it where you're taking your center of gravity, or where you're taking your torques around, which could be the center of gravity, and then start pushing down or pushing up. at the point where those forces act, and you can see whether it rotates clockwise or counterclockwise, because torques are rotational. So your pluses and minus totally come from it being turning it counterclockwise or clockwise. Fair enough?
Yeah, it's just because I had the like when I'm trying to imagine like pressing down, it feels as if like I'm trying to extend my triceps, if that makes sense.
Not really. If I put, are you trying to make this guy right here, the force of the triceps act in the opposite direction?
Yeah, because that's kind of how so I do it just the opposite direction for the triceps in order to solve it.
It won't solve it. It will give you a negative value. It will give you a negative value if you do it that way. It should give you a negative value if you do that way, because muscles can't push, right? Muscles can only pull. And if I had the triceps acting in that direction, if I did, where would the insertion be? Like the origin is actually at the elbow, and then it's inserting down in the air somewhere. So it can't do that. It has to pull. And my shoulder's up here, right? If my shoulder is up here, then my triceps is going to pull from here towards my shoulder. And so that's the direction it's going to pull. But it creates the same direction of rotation as this guy, because it's actually causing a rotation around the elbow, and the elbow is to the right of it. I mean, literally hold on to it here. If I push up here, I'm going to get the same direction of rotation as if I push down here. And it's the direction of the rotation that's important, not the direction of the force. Does that help?
Yeah, so it's only because of the position, is that correct then? That causes the rotation. So even if the force is upwards, then it will cause a rotation in clockwise direction.
Yeah, you
Okay.
got it. That's it. Okay. So stopping the share. I guess people are talking among themselves. There was one other, let's see. Additional problem 8. No, sorry. Yeah, 6 and 8. The man carrying the board. Yes. That is one that would be on it. So let me just do that one. We'll share the whiteboard again. And so this is chapter 13, additional problem 8. We have a board. We have a 1.8 meters. We have a fulcrum. And that fulcrum is at the shoulder. Okay, it's rocking back and forth over the shoulder. And that is 1.8 meters. And the actual center of gravity of the board, because it's a uniform board, you sort of, and it actually says that, assume the weight of the board is evenly distributed throughout the weight. It's a 3-meter board, so the center of gravity is going to be there. That's the weight of the 32 newtons. And that's going to be at 1.5 meters. Why 1.5 meters? Because it's a 3-meter board and it's uniform, so the balance point is going to be halfway, which would be 1.5 meters. Therefore, the difference between those two is 0.3 meters. On this side, we have a force of the hand, and again, this isn't to scale at all, but that is 0.2 meters. So this is a classic, at this point, it's not even a full free body diagram because I'm not showing the forces at the fulcrum, but just look at this and think a lever, a first-class lever, a teeter-totter. On one side, you have the force of the hand. On the other side, you have the weight of the board, and they have to balance. So on one side, you have 32 newtons times 0.3 meters. On the other side, and that has to equal to balance like a teeter-totter when they're balanced. 0.2 meters times the force of the hand. So you can solve for the force of the hand. 32 newtons times 0.3 meters divided by 0.2 meters, which is, I believe, 48 newtons, sorry. So that's how much force you would have to have on the hand in order to balance it. Any questions on that one? Okay, I believe Jenny, you were next.
I can please go over chapter 13, intro problem 10.
Chapter 13, intro problem 10, okay. Oh, so the friction one isn't there. I apologize. I will try and get that friction one. Intro problem 10. Okay. Did you want intro problem 7 too? Is that, you wanted both?
No, that was not me.
Okay, that wasn't you. Okay. So intro problem 10, which is given the following data for the reaction board procedure, calculate the distance from the platform support to the subject's center of gravity. Let's go to so we have a support at one end, and we have a scale, the force of the scale at the other end. And we have the person's weight. The force of the person. And on one side you have a length here of 2.5 meters. And over here, that's what you're looking for. That is the distance from the person's center of gravity to the support. So again, we're in a balanced situation where the torque being created by the scale is equal to the torque being created by the person, which means the force of the scale times its length is going to equal the force of the person. That's what's happening. That's what's happening in this balanced scenario. So we know this, we know this, we know this, we need to know that. That's what the question's asking you for. So D is going to equal a 600 Newton. Oh, sorry, I take that back. I am doing it backwards. It's going to equal a 2.5 meters times the force of the scale, which is 400 newtons, all divided by the force of the person, which is 600 newtons. So it's going to be 2/3 of 2.5, which hopefully is 1.67. Somebody can plug that in and just confirm. So that is going to be the distance from this rotation to where the person's center of gravity is. Now, you need to know where the person's feet are with respect to this too. So somewhere in here they have feet. And therefore, when they're lying there, and you know where their center of gravity is, let's say their feet are 10 centimeters from that rotation, then you'd know that their center of gravity would be 1.57 meters from the bottom of their feet. If you want to take that extra step and switch it. But the question only asks where it is with respect to that rotational piece at the end. Any questions on that one?
Okay, so in the textbook, the equation it took in the account the weight of the table. So in this case, we didn't need to do that.
No, you didn't have to, and I know it does in the book. It gives you the full equation. And so you might be wondering why it doesn't do it. What happens in this kind of questions, if you were actually doing this in person, you would zero the scale before the person got on it. So the force of the scale, if you have the board sitting on here, on the scale, pivoting around its point, and you have it sitting on the scale, what you can do is you can zero it before the person comes on, which means that you've taken away the effect of the board. So you literally, I don't know if any of you have a kitchen scale, and you will put, and it allows you to shift. I have a kitchen scale that does this. And I want to find out what the, a certain amount of butter that I want to, and it's given me the ingredients by weight. So I put a bowl onto my scale and then I zero it so that I know when I add the butter to it, all I'm looking at is the mass of the butter. And I'm not having to take, okay, I put a 0.2 kilogram bowl on there first. So whatever I get, I have to subtract 0.2 kilograms off. I don't do that. I put the bowl on, and then you can shift it around till it's 0 with the bowl on it, so that you know that when you put the butter in, only the butter is taken into account. That's what happens in these kinds of scales, is you put the board on, put the scale on, and then you 0 it with the board on it, and that takes into account the weight of the scale, of the board, sorry, the weight of the board. So that you know when you put the person on it, it's only the person that you're worried about. Does that help? They just don't tell you that, which I think is kind of misleading after they give you the full, complete equation in the textbook. But
Yeah, that's why I was confused, but I get it now. Thank you.
any other questions on that one? Okay. Oriana.
Okay, so I have a question about in chapter 12.
Yeah.
The introductory problem 10b.
10b. Introduction problem 12 in chapter 12 or chapter 12. Oh, what was it? 10b?
Yeah, 10b.
Oh. So, a pitch ball with a mass of 1 kilogram reaches a catcher's glove traveling at a velocity of how much impulse is required to stop the ball? You know what? I mean, I can answer it, but we haven't done momentum yet. And the reality is, all I need to tell you is that whatever you find for the linear momentum, that's the amount of momentum, which is an amount of motion, which we haven't done and won't be on the midterm. If you calculate how much momentum you have, which is mass times velocity, which is the 28, which is part A. Impulse is force times time, which happens to equal the same units as mass times velocity. And however much momentum it has, which is a quantity of motion, it takes that much impulse to stop it, because then you're getting rid of that momentum. Does that help?
Yes.
Okay. I'm jumping ahead there, and I don't want to go too far down that rabbit hole because we haven't got there, and I haven't posted the lectures, but
Okay. That's why it was a little confusing, but okay. Okay. Thank you.
That's not going to be on the midterm. We haven't got there yet. Final, yes. Midterm, no. Danny.
Hi, Professor. I was wondering if we could do additional problems on chapter 12, number 3.
Number 3. Oh, I like 3. 3 is a good friction one. And again, allows us to talk about what friction does and doesn't do. So
Yeah, that's what I was hoping I could talk about. Thank you.
So we're going to share our board here, and I'm going to go into I'm going to see my ceiling again. Okay, so we have, this is chapter 12, additional problem 2, a 2 kilogram block sitting on a horizontal surface is subjected to a horizontal force of 7.5 newtons if the resulting acceleration of the block is 3 meters per second squared. What is the magnitude of the friction force opposing the motion of the block? Let's start with a free body diagram. Very important. We have a block. That block is sitting on a horizontal surface. And it's obviously going to have a weight. It's going to have acting on it a horizontal force, which is really, if you go back to the friction lecture, that is the applied force. So that horizontal force is the force that's the applied force. I'm going to have two components of my ground reaction force, the force that's acting underneath this block, and that's going to be a normal force. And if you were using the nomenclature that the book would use, that would be the same as R. And I'm going to have a force that is along the surface. So this one is perpendicular to the surface, and this one is along the surface, and it's going to be my frictional force. And I'm going to have an acceleration in that direction. So that's the acceleration in the X direction. Let's just do this because we have X, we have Y, and we have theta, and that's the directions that I'm considering positive here. So we have, let's just look in the Y direction to begin with. First of all, before we do anything, weight equals mass times gravity, which equals 2 kilograms times 9.81.
Sorry, Professor, there's a lot of static noise.
Is everybody getting static noise?
Yeah, I hear it.
It's gone now.
Oh, now, okay.
It has to be when you put the...
It's when I put it down. Let's try that. How's that?
That's good.
Okay, so that's somewhere in between. I guess there must be something underneath. Yeah, I bet it's the fan. Anyway, doesn't matter. So this is going to be 19.62 newtons. Fair enough. Anything I do mathematically in my head, feel free to check and see if I got it wrong, because it's quite possible. So if I take the sum of my forces in my Y direction, that's going to equal the mass times acceleration in the Y direction. This is what we know from Newton's second law. And this is really as much a friction question as it is a Newton's second law question. So the force in the Y direction, well, it's on a horizontal surface. It is moving in a horizontal direction. There is no movement in the Y direction. It's not moving up or down. It's going along a horizontal surface, which means this is 0. There is no acceleration in the Y direction. So I have my force, normal force, which is acting up, minus my weight force, which is acting down, based on my center of what I consider positive in the Y direction. That's going to equal 0. So the normal force is going to equal the weight, which equals 19.62 newtons. You don't actually need to calculate that, but we're doing it. So if we look in the X direction, sum of the forces in the X direction equals mass times acceleration in the X direction. Okay. What forces do I have? I have this guy acting in the positive direction. This is guy acting in the negative direction. Why is it acting in the negative direction? Because I know it's moving in this way. If it's moving to the right, then the friction has to be acting to the left. So the horizontal force minus the frictional force equals mass time, well, let's see, mass, might as well put the mass right in there. The mass, which is 2 kilograms, times the acceleration, which is 3 meters per second squared, because this equals 3 meters per second squared. That's, we're given that. So we know H, that is 7.5 newtons. We know everything else here. The only thing we don't know is friction. So we rearrange this equation so that the force of friction is going to equal 7.5 newtons minus 6 newtons, or 1.5 newtons. So that's all you needed to do to answer this question. And it's a combination of understanding friction and understanding Newton's second law. But we can do so much more with this question. So I'm going to ask the question, is this kinetic friction or is this static friction? Any thoughts?
It's kinetic because it's moving.
That's right. So this has to be kinetic because it's moving. By definition, it is moving. What is the coefficient of kinetic friction? We don't know, and we couldn't calculate what the coefficient of static friction is because we don't know at what force it started to move. But we know that it's moving. It has to be moving. If it wasn't moving, if it wasn't moving, there'd be no acceleration. So this kinetic friction coefficient, let's just remember what friction equals the times the normal force. Remember, that's just my symbol for normal force. They use R. So if we wanted to calculate, not that they give us this answer, but again, these are the kinds of things you can do with the next steps of questions. That means that this coefficient of kinetic friction is going to equal 1.5 newtons divided by 19.62 newtons. So whatever that is the coefficient of kinetic friction between these two surfaces, the box and whatever surface the box is sitting on. Any questions on that? I'll let you plug that into your calculator, but. Everybody good with that one? Again, you have to unmute and ask because I don't see chat when I'm sharing. Okay, I will clear that canvas, stop the share. Sahel, I hope I pronounced that okay.
Yeah, that's right. Can we do chapter 13, introductory problems number 7?
13, the mechanical advantage one?
Yeah.
Okay, so absolutely, it's a good one to just think of. First class lever, I mean, the short answer is it can be all three. But let's just think about that. We'll share it again. So first class lever means that we have our fulcrum in the center. Don't mind me. I'll buy the board. I'll draw the board first. So we have our board, our lever arm. We have our fulcrum, and we have on one side our applied force, and on the other side our resistance force, right? Just flip back. To what they give you, for because it's a little different than what I do. Yeah, applied force and resistance force. And you have a mechanical advantage. Sorry, there is a distance here, which would be the resistance arm, and the distance here, which would be the force arm. And this resistance is the load. That's what we're trying to move. It's the force applied by whatever we're moving. So mechanical advantage is going to equal the force arm divided by the resistance arm. Make sense?
Yep.
If the reality is this fulcrum can be anywhere along here. It could be here, in which case the force arm would be really small compared to the resistance arm. Or it could be here, in which case the force arm would be really big compared to the resistance arm. If it's right in the middle, then the force arm is going to equal the resistance arm, and your mechanical advantage is going to be 1, right? Make sense?
Yeah.
If it's over here, then your force arm would be small compared to your resistance arm. And the so RA would be big, FA would be small, and if it's way over here, your mechanical advantage would be less than 1. That makes sense?
Yeah.
Okay, let's say you were using a pry bar. And here is the load of what you're prying, which is the resistance force, or R. And you put the fulcrum here and are pushing down here. Do you think that's a good situation? Do you have to push more than the actual resistance? So this is a situation where mechanical advantage is definitely less than 1 because this distance is smaller than this distance. So you have a mechanical advantage less than 1. If you were trying to pry something, would you hold the pry bar really close to the fulcrum.
So we need like more force to do the
Exactly.
same work.
It would mean that the applied force would have to be, if the mechanical advantage is less than 1, that means the applied force will be greater than the resistance force. Which means if you're using this lever to help you, it's not helping, because you actually have to apply more force than you would have if you just picked the rock up yourself. You actually need to use more force than if you had just picked the rock up yourself, because you actually have to apply greater force than the actual force of the load in order to move something. Now, this is an advantage if your load is and this is the situation you want to be in if your load is really light compared to what you are. So if you're talking about a teeter-totter with a kid and you're an adult, this is actually the situation that you would want to be in, because by definition, the adult's weight force is going to be greater than the load, which is the kid's weight force. And so you put the child way out here at the seat, and the adult often has to sit here in the middle in order to be able to balance it, right? But if you're using this lever to pry a rock out of the ground, this is not the situation you want to be in, because you actually have to apply it. And so that's a mechanical advantage less than 1. If, however, I put my fulcrum here, and here's my stone that I'm trying to pry out of the ground, which is my load, and here's my applied force. In this case, this guy is going to be larger than this guy, and therefore my mechanical advantage is going to be greater than 1. Okay, so this is mechanical advantage greater than 1. And in this situation, when the mechanical advantage is greater than 1, that means that the applied force that I need to apply is going to be less than the load itself. That, if I'm trying to lift up a rock, if I'm trying to pry a rock out of the ground, that's a heavy rock, this is an advantage. So when my mechanical advantage is greater than 1, that means I do not have to apply as much force as the actual load that I'm trying to resist against. Okay, so the resistance or the load can be less than how much I have to apply, which is excellent. That means I do not have to push down as hard as I would have if I just even picked the rock up straight. It means I can use less force. So this is a big advantage, which is why it's called mechanical advantage. When that mechanical advantage is greater than 1, we are in a good situation where we do not have to apply as much force as as the load that we're trying to pry out. So that's first class lever can have mechanical advantages less than 1, equal to 1, and greater than 1. Not true of second and third, but this question asked you about first. And so there you go. That help?
Yeah, very much. I also have another question on chapter 12, but it's like momentum related. So we're not responsible for that now?
Not responsible for momentum for the second midterm. It'll be on the final.
Okay.
Okay.
Thank you.
You're welcome. Okay, anybody else have questions about this before I clear? Okay. Elia?
Hi, Dr. Moore. Can we please do chapter 12, additional problem 8D?
8D.
Mhm.
12A 8D. Okay. Okay, so this is a question. A 50 kilogram person performs maximum vertical jump with an initial velocity of 2 meters per second, which you can do using energy, transfer of energy from kinetic to potential and then back to kinetic. You can do it that way. And the question actually is asking you to do it that way, but since we're not going to do it, cover energy, I'm just having you do part D, which you can do just as easily with projectile motion. So we'll just quickly do it using projectile motion. So essentially you have something, a person in this case, going up and back down. And they're going, when they take off, their initial velocity is completely vertical, 2 meters per second, and yeah, it's 2 meters per second with a 90 degrees, so perfectly vertical, which means you want to find this. Vertical. So you can solve that problem if we go back to chapter 10, page 323. Where we want to figure out the height given the initial velocity, which will be that probably is bothering you guys again. Sorry. It's just easier for me to do on the ground. So D is going to equal V squared over 2 times 9.81. I'm just getting rid of the negative. The negative that I would have got there gets rid of because of that negative right there. That's meters per second squared. So it's going to be 2 meters per second, all squared, all over 2, 9.81 meters per second squared. And if you look at that, it's going to be, I'll have meter squared divided by second squared. The second squareds will cancel and I'll be left with 1 meter, which is exactly right. So 2 divided by 9.81 is, I'm just doing 2 squared divided by 2 is
0.2 meters.
Is 0.2 meters. Yes.
Mm-hmm.
Or 20 centimeters, which they throw in there. So we did that completely using projectile motion, the initial velocity and initial vertical velocity. We knew which direction it was, what magnitude it was. And it's just projectile. It goes up 9.81, comes down. So it hits the apex where the velocity equals 0. So here it equaled 2 meters per second, and here it equaled 0. Any questions on that one?
So for the midterm, then we don't, because the textbook used the equation PE plus KE equals 100 joules. So we're not expected to know that equation, right?
You do not need to know that kinetic energy equals potential energy. Kinetic energy at the top, at the bottom, equals potential energy at the top. No, you don't need to do it that way.
Okay, thank you.
You do not need to know the, kinetic energy equals 1/2 mass velocity squared. And interestingly, you start to see in this equation, it actually has all the things that are in those equations are actually in here, because you've got, if mass times velocity squared, and the masses cancel because mass times g is in that one, and the v squared divided by 2 is in that one. Really, it's just the fact that the mass is squared. Everything else is in there, but no, you don't need to know it from energy. Okay, so I'd love to have that time. It was always the question, it was always the section of the course that I had on the very last lecture, and we never got to it. So I've decided that I wanted to spend more time, or the time that I was spending on stuff, and then just take it off. Okay, Elena.
I have a question. In our midterm one, first midterm, we had a question about Paralympic.
Yeah.
So it's like speed and displacement. Could you come to this one again?
Again, I was going to say I did go over it.
Yeah.
No, I went over it. So I don't have it right with me. The day I did go over it in tutorial. But the reality is the horizontal. So you've got something that's moving horizontally, right? Such as you would have seen in question 10, additional problem 10, number 1, chapter 10, additional problem number 1 is something moving in the X direction, right? It's the runners, but they're moving in the X direction. So you would have seen, basically, there's a marker at the bottom of the ski pole. And so if you are at all pulling your skis, you put your pole into the ground, and then you use that to rotate. It rotates around, but you can see my hand is where my hand is holding onto the pole, and where I have it pinched at the bottom here is the pole, bottom of the pole. And so you put it into the ground, and then you pivot. Then you lift it up, swing it around, put it into the ground, and then pivot again. And that's what you do with the pole. And so what would happen horizontally, we're only looking at the bottom of the pole initially, is you're going to see it go forward. Oh, sorry. Again, we have X, and we have time, and we're going to go forward. We're going to hold, because that's where it's planted in the ground. When it's planted in the ground, it's not moving anywhere. and then it's going to go forward, then it's going to hold, and it's going to look an awful lot, with the exception of these hold portions, it's going to look an awful lot like Ben Johnson and Carl Lewis running. The only difference is that it's got these hold portions where it stays at the same X for a period of time. That help? If you wanted to look at it for the Y portion, again, when it's at the same point it's here, it's just sitting on the ground. So those are givens. It goes up and it comes down. It comes up and it comes down. So it comes up and it comes down, comes up and it comes down. That help? Elena? Did I lose you?
Yeah, thank you so much.
Okay, that's what I didn't have it here to open like I did the day after or the week after the midterm, but that's essentially what it is, and it's just understanding that, you know, something that's on the ground goes up and it comes down, or horizontally.
Yeah, I was confused with it's horizontal and vertical, so that's why.
Yeah.
Now I got it, yes. Thank you.
You're welcome. Any other questions?
Not so a question, it's more like with the center of gravity, in the textbook example, they don't use like distal and proximal. They go directly to the center of gravity and they give the data. I was wondering if we are going to be provided, let's say, the similar data on the midterm, or do we have to be able to calculate it directly from, let's say, a table? It's like 13.7.
Like 13 point, like the one that
There's sample problem 13.7.
Yeah. I could do it either way. Often, I mean, if you're doing it in real life with people, you pretty much are doing it from. So the question is really what you're asking me. Do you start from the joint centers, or do you start with already being given the center of gravity, knowing the joint centers? And the question is, it could go either way, because from the joint centers is an important skill with anthropometric data, knowing that's how we estimate. I mean, I can't tell you where the center of gravity of my forearm and hand is just blindly. I have to estimate it somehow. And so that is the way we tend to do it, is we use anthropometric data to say, well, in general, it's, you know, this percentage of the way along here. So given the X and Y coordinates of where my elbow is, and given the X and Y coordinates of where my wrist is, I can estimate where that center of gravity is of my forearm. And that is how we do it in general. If you're working on a gait analysis of, you know, with kids in a gait lab, it's probably embedded into the into whatever software they might be using, but that's how they figure out where the center of gravity of a particular body segment is. And so I have shown you the whole way, going from joint centers then using that anthropometric data to figure out where the center of gravity is, the XY coordinates of the center of gravity are. And then once you have the center of gravity of the each of the segments, how do you combine those segments together to get the center of gravity of the combined segments? Both are important skills. This question is really just emphasizing how you combine. Once you have the center of gravities of the segments, that's how you combine them. But the fact that you have to actually figure out where the center of gravity is of a body segment, although they don't show an example necessarily on here, they do actually have the tables in the back of the book that allows you to do that. I'm pretty certain they were there. So if you look at chapter D, it gives you the segmental center of gravity locations, which is percentages of the segment lengths measured from the proximal end of the segments. So clearly in the book, they recognize that that's an important skill.
So will we be given that table, or we have to look it up?
Typically, I give you the data. You know, so the center of gravity of a thigh is 4.3% of the distance along for a male, along the segment length of a thigh. So I would give you that information.
Okay, thank you.
You're welcome. And clearly, if I did it in a table, I would give you a table that you would have to look it up for, but one way or the other, it would happen. Any other questions? Okay.